Hello, everyone, and welcome. My name is Ian, and in this video, I'm going to be talking about some of the foundations of statistics and probability and working with data. And to start with, I want to talk about random variables, or the idea of mapping events to numbers. So just to start things off with some food for thought, let's say we want to throw a six-sided die, and we want to describe this process mathematically. And if we wanted to, we could use, say, Newtonian mechanics to talk about the forces and momentum and the velocities and the rotation and elastic bounce and all the kind of physical things happening as this die is being thrown through the air and bouncing off of surfaces. So this is one approach that you could use to model a die throw. But in statistics and in a lot of data analysis pipelines, we want to simplify a system to be represented with much less information or fewer numbers, fewer calculations. And random variables give us a way to do this. So one of the most intuitive ways that you might want to model this die is just to talk about the outcome as a single number. And so we could have, say, a sample space here, and usually you represent this with the Greek character omega. And we would say that if we were to perform an experiment, you have one of 6 possible outcomes. And using a random variable, we would assign each of these outcomes a number. So in this case, our random variable x is this set of 6 numbers here, each of which corresponds to an event of the die roll. And here we've simplified this kind of complex process of, a bundle of atoms and bouncing around. And so there are many ways that you could get, say, a 2 result if we're being literal and talking about the physics of throwing a die. But for the purposes of this model, we're going to say that there's only one event corresponding to a 2, and that's 1 in 6 possible other events. And another example of a random variable might be a coin flip, for example. So we could assign a random, we could assign a number, a 0 or a 1, to the result of a coin flip. And a lot of times you will have random variables that are built off of other random variables. And so we could create another random variable that is the sum of the result of multiple coin flips here. So here we've assigned the result of one coin flip to be either 0 or 1, depending on whether it's heads or tails. And we have, instead of our random variable taking on values of 0 or 1, let's say we have a different random variable, and that is going to be represented by adding up these quantities from multiple coin flips. So maybe we're talking about 8 coin flips or 9 coin flips. And the thing you'll notice is that we've reduced the complexity of this system. So maybe in one experiment, we do multiple coin flips and we sum them up, we get a 5. In another experiment, we get a different permutation here of results, but the sum is still 5. And in this way, we've mapped multiple events to one number here, one outcome, 5. And this is going to be a basic property or key property of random variables in general, that they're kind of simplifying many events. And this is also the case when we think about the single die throw, right? So we had the Newtonian model, and you can imagine we throw the die once, it bounces off some atoms, experiences some forces as it hurtles through the air. and after 3 bounces, it rolls up with a 3 facing up. But we repeat the roll. Maybe we do it another time. We throw it at a different angle. It bounces 4 times instead of 3 times. Bumps into different atoms. But again, ends with the 3 facing up. And in our simple model, we treat those as the same event, even though if we're being literal, if we're talking about kind of microscopic model, they're actually different, very different processes that led to that result. So yeah, and then we can do this for the multiple die roll example as well. So we could have, say, a random variable that corresponds to the sum of multiple die rolls. In this case, we have an example which is the number of even results. So we do multiple die rolls and then we count how many of those were even. Yeah, that's just another type of random variable. So it can take on different results, and what makes it random is that unlike an algebraic variable, there is randomness inherent in the process. So we cannot just calculate what you're going to get. We have to introduce this element of randomness. And so that brings us to the idea of probabilities. So when you have a random variable, there's going to be a corresponding probability distribution that is connected to that random variable. So we've mapped a bunch of events from a sample space to some numbers, that's our random variable, and then we have corresponding probabilities to describe when those events occur, how often they occur. And in the case of this fair 6-sided die, we can calculate the probabilities easily by noticing that there are 6 total events possible. And if this is a fair die, then the probability of any one of those events is simply going to be 1 divided by the total number of possibilities. So that's 1/6 in this case for all of these events. But what if we have a biased die? For example, like this, we have 1 through 5 possible events that correspond to probability of 1/10, and then the 6, rolling a 6 has a probability of 5/10 or 1/2. And you'll notice that we still have 6 possible events here. So we can't use our earlier trick of just dividing our event by the total number of events here. So how do we deal with this? Where does this come from? And what happens to our model when this is the case? And so to kind of understand this, it's good to go back and think again about this idea of simplification, and that one event in this system actually corresponds to a collection of possible events. And so we might say that there are 6 possible events, but each of those events corresponds to a giant, say, infinite space of ways that you could roll, for example, a 5 here. So this is, every path through reality, or every path, chain of cause and effect that leads to the result being interpreted as a 5. And then we've gathered those all into one space and assigned that the name 5. And so it could be, it bounces 3 times and rolls up 5. It bounces 1 time, and that's another way to get a 5. And all of these map to the same event. So yeah, if we want the probability, we're dividing the size of this event space by the size of the total space. So we're doing essentially the same thing we did in the first case, in the 1/6, where we took, there's 1 possible event, we divided by 6 possible events. But now we're taking an infinite possible ways to roll a 5, say, and dividing that by the larger infinity of ways to roll anything else, including a 5. And you might be thinking, how is this possible? Infinity divided by infinity, does that even make sense? And it turns out infinities can be different sizes. So one way to think about this is like, let's say I paired up integers. So if we had all the integers as one set, then we can imagine another set where I'm multiplying the integers by 2. So we have one set on the left here, all the integers, and then another set, all the integers multiplied by 2. And obviously, both of these are infinite, right? There's an infinite number of integers. There's also going to be an infinite number of integers multiplied by 2. And in this case, we can map 1-to-1 or connect 1-to-1. For every integer, we can pair that with its counterpart itself times 2. So in this case, this is an example of a situation where the two infinities are the same size, but infinities can be different sizes. So, I can say, what if we take an integer and pair it, or let's consider the set of all real numbers, and then compare that with just the set of integers. And so if I try to do this pairing thing again, I would see that for every integer, there's already an infinity of possible things to pair it with in the real numbers. So, 1 pairs to 1.01 or 1.001, and so on, before we even get to, real numbers between 2 and 3. So we've already got an infinity corresponding to this one guy. So this infinity on the right here is larger than this infinity on the left. So that's sort of a way you can think about this, and so we can kind of figure out, or sort of conceptualize at least, what is going on when we have a biased die. So if we have a biased die, we're saying that the space of possible events, say the ways you can roll a sixth, we said was 5/10 in the biased die, and then it was only 1/10 for the other ones. And so this is basically just saying, we're saying that there are more possible ways more paths through reality that bring you to a 6 than there are that bring you to 5. Or for every one path through reality that brings you to a 5, there's going to be 5 ways that take you to a 6. And so even though everything's infinite, there's an infinite ways to roll 6, there's infinite ways to roll a 5, there's a larger infinity of ways to roll a 6. And then when we think about how big that is compared to the space as a whole, like all the possible events, all the results of rolling this biased die, well, then it's 5/10, so roughly half of the total space. So this is discrete random variables. So in this case, in the case of a die or a coin flip, these are countable random variables in that we can count the even if it's infinite, like the set of integers that you could get, the set of sums that you could get from die rolls, it's still countable. But we have continuous variables, random variables, and this is things that are not countable. So, for example, length can take on any value within some range. So, for example, the length of this leaf here, it can be 3.67983 centimeters or 6.7989158 centimeters. There's an infinite range of possibilities that we cannot count. Another example would be, say, an angle or a volume. All of these are quantities which can take on an infinite number of values along a continuum. And so here's maybe a more practical kind of scientific example of a physical system. Say we have a beam here that's passing through a liquid sample that contains some dissolved molecule, and we're passing that beam into a detector that's giving us a value It's telling us how much of the light has been absorbed as it went through the sample. And in this case, we have a random variable that corresponds to that absorbance. And this can take on any number of values. So for example, we could have an absorbance value of 1.101359. We could have a value of 1.11935. The thing to note here is that there's still a simplification taking place, right? So even though you can take on infinite values, we could have a very highly specific value of the absorbance here. It's still just one number describing a complex process, right? This beam passed through a sample, bounced off, scattered light, got absorbed by different molecules, billions of molecules, and passed through the air on the way. So there's all these events that are kind of reduced when we produce this final number. And you can imagine for each of these numbers, there is still a kind of infinity of different ways that reality could map to that number. And then the thing with continuous random variables is we describe them with ranges. So if we ask, what is the probability that we get this particular result here? And the answer for continuous variables is that it's always going to be 0 because there's an infinite number of possibilities. And therefore, if we want to talk about the probabilities associated with a continuous random variable, we have to talk in terms of ranges. So what is the probability that x, our random variable, lands between 1 and 1.1, and then we can get a finite number in that case. So here is just some examples of continuous and discrete random variables. So the time between cell divisions, so time is a continuous quantity, even though cell divisions might be countable. Time itself can take on an infinite number of values along the continuum. So that's a continuous variable. If I ask you the number of cell divisions in a 1-minute interval, so we've kind of flipped this first example around. Well, now we've used the word number, and so it's going to be discrete, right? So we can count, we're counting cell divisions, and that makes it discrete. If I ask you the number of molecules binding to a particle, once again, we've got that keyword number, and that's going to indicate to us that this is countable. So if we're counting molecules, even if it's a lot of them, that's still going to be discrete. Distance between molecules on a surface. So trying to keep things a bit tricky here. So, of course, we can count molecules on surface, but if we're talking about distances, that can take on any number of an infinite number of possibilities. So that's going to be continuous. If I ask you about the fluorescence intensity from a microscope image, so fluorescence intensity, in most cases, this is going to be continuous. But I could get tricky here and ask you, say, the number of photons landing on a camera pixel, which is almost the same thing as asking the fluorescence intensity from a microscope image. But of course, if we're talking about the number of something, in this case, photons, well, that's going to be discrete. And so, yeah, there's a bit of a gray region here. So, and this happens with a lot of things, right? So if we talk about volume, we gave that example earlier and said that's, of course, continuous. But number of water molecules in a box, maybe this is very similar to asking what is the volume in the box. But as long as we have this number, this keyword number here, then that's going to be a discrete variable. So sometimes the size of your system, if you're down to the quantum level, then things that maybe you would normally be thinking of as continuous start becoming discrete. So yeah, to kind of just wrap things up here, we have this idea of random variables, and this is the idea that we're going to map a event in reality or a set of events happening in reality, and we're going to map those to numbers. We're going to represent them with numbers. So it's a kind of model, and they can be discrete or continuous. And then the thing about this random variables is, right, we have this keyword random. They're not the same as algebraic variables that you can just calculate them. So we're indicating that this is a process that the result can change from experiment to experiment. And to describe this uncertainty, we use probability distributions, and these emerge from the relative proportions of possible events, or the size of different parts of event space, you could say, and trying to count those up and compare them with each other. That's how we get probabilities.